Welcome to POE. Today we're going to be talking about centroids. Centroids are a way that we deal with basically kind of finding the middle. Centroid principles. Object's center of gravity or center of mass graphically labeled as this little symbol right here. And what that's telling us then is that's the centroid. That's where it will balance. Centroid principles. Point of applied force caused by acceleration due to gravity. Object is in a state of equilibrium if balanced along its centroid. So here, this would be pointing to its centroid. This would not, because it's not balanced. What is an object's centroid location used for in statistics? Well, theoretical calculations regarding the interaction of forces and members are derived from the centroid location. I want to point out that this is theoretical, meaning this is not tested data, this is calculated data. So it's not always going to be 100% accurate, but it gives us a very great way, a very great position to start with. One can determine a centroid location by utilizing a cross-sectional view of a three-dimensional object. Symmetrical objects. Centroid location is determined by an object's line of symmetry. So if we're looking at just one object, all you have to do is find its lines of symmetry, and that's going to tell you where the centroid is located then. What they don't show us over here on this rectangle or this triangle would be drawing lines through there. All right. Probably, I guess, because those aren't really lines of symmetry, but those would also be lines going from center to the other end there. At any rate, centroid location. Well, this is important. Hopefully you guys are listening to this and not just copying stuff down. Centroid location for a square is half of its height and half of its base. Right? Half of its height and half of its base. For a square or a rectangle. When it comes to a triangle, all right, specifically a right triangle, it's a third of its height and a third of its base. And virtually everything, a lot of times we can turn into a right triangle with a little manipulation. When it comes to a semicircle, what we do here then, again it's for a semicircle, is we take 4/3 4r over 3 pi. And they give us an example here of how to go about doing that. These are our equations we're going to be using to find the location of the centroid. In every three-dimensional object there is an x component, a y component, and a z if you think about the three parts of an axis. We have the y, the x, and then we have this z component. So this would be our x, this would be our y, and then we have a z-axis as well, giving us 3 dimensions. So that's why we have 3 equations, x, y, and z. But each component is essentially found the same way, just using the different ordered pairs, or ordered triplets, I guess, in this case. Okay, what we have here then is an irregular shape, but we've divided this into 3 very simple shapes. We have a square over here on the left. Alright, or a rectangle actually. I don't know why I said square. There's our rectangle. Here's our square. And then right here's a right triangle. So we know how to find the centroid for each of those locations. Calculating area. Well, why are we calculating area? Well, if we go back to our equation here, area is a huge factor when it comes to finding the centroid. So if you have questions on that, you'll need to get this down. I'm going to go over that part pretty quickly here. Now, finding the area. Well, we've kind of helped you here with this. When it comes to finding the area of the shape 1, shape 1 is over here. It's a rectangle. It's the width times the height. Width times its height. It's 3 times 6, which gives us 18 inches squared. Area of shape number 2, that's the triangle over here. Well, that's the base. The base here is 3 inches. The height is 3 inches. So it's half of that. 3 times 3 is 9. Half of that is 4.5 inches squared. The last one then is to find shape 3. What's a square? 3 by 3, or 3 squared, gives us 9 inches squared. Hopefully we're past that part. Determine the centroid of each simple shape. Well, to do that, we put in our lines of symmetry, and they've already done this for us. Right? They've already included our lines of symmetry here, and from that now we can locate them. Obviously, in the rectangle, it's half of the height, half of the width. In the square, it's the same thing, half the width, half the height, or half the side, I guess they would probably actually say. And then for a triangle, it's a third of the base and a third of the height to find that centroid where it's going to balance evenly. Alright, determine the distance from each simple shape centroid to the reference. Alright, well, what we've done here is we've put in a reference axis, and that's right here. This is one of the most important parts. Give yourself an X and Y axis to start with. Alright, let's pick blue. We'll do blue because there's our reference. It's in blue here. Now, the centroid is over halfway. Well, what's half of 3? 1.5. It's halfway up. What's 6 inches tall? So halfway up would be 3 inches. The square is over 3 inches plus halfway again. That's 1.5 inches. The 3 plus the 1.5 inches gives us 4.5 inches. Right, that's over here by 3 plus 1.5 inches. Likewise, this is just halfway up 3 inches, so this right here is the 1.5 inches. Well, we know that the triangle is a third, so if this is 3 inches, then we know that from here to here is 1 inch. We know from here to here is 3 inches. 3 plus 1 equals 4 inches. So that's where we get that dimension there of 4 inches. Multiply each simple shape's area by its distance from the centroid to the reference axis. All right, so we're going to be doing this in both the X and the Y dimensions. So in the first one here, all right, shape 1 in the X direction, its centroid here is 3 inches, all right, 3 inches from our center point here. Which turns out to be 54. Shape 2, all right, well, how far over is it? It's 4.5 inches. And these are all per the instruments and the measurements we had done from the previous slide. That turns out to be 20.25. The next one, it as well is over 4.5, or sorry, it's over 4 inches. Well, that gives us 36 inches. I'm going to do the same thing for the Y's. The Y, its centroid is up 3 inches. Gives me 54.0. It's not always going to be the same. The Y then for the second one, it is up 1.5 inches, which gives us 6.75. And then the third one is up 4 inches, and that's 36. Now, as I've looked back here, something didn't seem quite right. If I go back here to the first shape, along the x-axis from here to here, I've got listed as 3 inches. It's not 3 inches. It's supposed to be 1.5, so I need to change those measurements. Okay, I went ahead and changed those, and we get 27.0 for that. I actually had to make quite a few changes here. I had noticed that I had switched my shape 2 and shape 3. I was using all my measurements for shape 3 to be, and I was putting them in up here for shape 2. So XI, shape 2 is actually over 4 inches, so I changed that to 4. And then shape 3 is over 4.5. Down here, shape 2 is up 4 inches. Shape 3 is over 1.5 inches. I apologize for making that mistake. Probably several of you had already caught that or getting ready to say something to me about it in class anyways. Well, next part of this. Sum the products of each simple shape's area and their distances from the centroid to the reference axis. So what they're telling us to do here is that very far right column. that far right column, this column right over here, right, this column right here, they're telling us to take the sum of all those numbers, and that's how we get here. And that's what we call the sum of AI, XI, and that's this top part. All right, that's going to be the top part of our equation. And then AI, YI would still be the top part in the Y equation instead of the X equation, obviously. In these two cases, they're the same. They will not always be the same. Not always be the same. For those of you who aren't listening, you have no idea what I just wrote not down there. Sum the individual simple shapes area to determine the total shape area. So again, down here at the bottom, we've got to add up now that this first column. They want us to add up this first column because that's the bottom part down here of the equation. The bottom part is we have to find the total sum of the area, and that's what we're doing here. We're taking these and adding them up. The nice thing you'll see is down here on the bottom of the equation, it doesn't matter if we're using the X, the Y, or the Z equation. It's the same in all three. It's just AI. It doesn't make a reference to X whatsoever at all. So once you have that, you only have to do it one time. And then you'll always have your bottom number for when you go to divide this. When you go to divide this, then, it tells us that the centroid is going to be 2.71 inches over on the x-axis, and then straight up from there, 2.71 inches on the y-axis. And what that then gives us, can't see it with that color pen, is it gives us this nice center line. This will give us a line of symmetry that runs right through the middle of it. Real quickly here, I just want to go over some of the common structural shapes and how they're formed. Imagine a block of metal, and it would be real expensive to be able to give you or to be able to sell a big sheet of this or a real thick member of this. So what they'll do is they make different shapes to give you structural integrity. One of the ones they use is an angle shape, an L shape. Basically, they cut out or mill out a middle section of this. They have another one here called a channel shape, which is a C shape. Right here, they cut out all of this part right here. They have a box shape. Right? You have two structural members on the right and left sides, but they cut out the middle part. And then they have an I-beam. I-beam is probably the one you're most common and comfortable with. Well, the centroid of these structural members, we're still going to look at a cross-sectional view of them. Right, we're still going to be looking at a cross-sectional view of them. One of the things I want you to see is if we take it and push on it, what we can see then is the red area is called compression. That means those particles are being pushed together. The blue part down here is called tension. Right? Later on this year, we'll deal with a thing called West Point Bridge Maker, and that blue and red will be obvious in the bridge where they'll be showing you the compression and the tension. Notice right here in the middle is our centroid. They've got our symbol for centroid. Well, hey, that's everything for today. I'll catch you guys on the flip side.